To understand the global nuclear fuel cycle, we have to look past the politics and go straight to the machinery. Today, we are analyzing the physics and engineering of uranium enrichment using researched expert texts. Stick with me through this entire sequence, because as the material becomes more refined, the engineering becomes increasingly dangerous. This comparison shows the scale of the energy we are talking about. On the left is a single kilogram of the isotope uranium-235. To extract the equivalent amount of heat from coal, you would have to burn through this 14,000 kilogram pile on the right. But natural uranium doesn't come out of the earth ready to power a city. It is mined and processed into this heavy yellow cake powder. In this raw state, it is essentially useless rock, incapable of sustaining a nuclear chain reaction. Harnessing the energy trapped in this material requires overcoming a specific physical hurdle found at the subatomic level. That powder consists almost entirely of two distinct isotopes. Over 99% is uranium-238, which is heavy and non-fissile. The isotope we actually want, the reactive uranium-235, makes up less than 1% of the total mass. This creates a significant engineering problem. Because these isotopes have the same number of protons, they are chemically identical. You cannot separate them by dissolving them in acid, burning them, or boiling them. Standard chemical extraction is entirely ineffective. There is only one exploitable difference between them. The uranium-235 atom has 3 fewer neutrons, making it a mere 1.26% lighter than its sibling. Because chemical separation is impossible, we are forced to rely on extreme physical force to sort these individual atoms by their weight. Before we break down the machinery used to do that, take a second to like this video and subscribe to the channel so we can keep producing these deep dives. You cannot apply fluid dynamics or centrifugal forces to a solid block of metal. To physically sort the atoms, the uranium must first be converted into a fluid state. Facilities achieve this through a hydrofluorination process, converting the solid material into a highly corrosive gas called uranium hexafluoride. Fluorine is used for a very specific reason. It only has one stable mass. When 6 fluorine atoms bind to a uranium atom, engineers know that any weight difference in the resulting gas molecules belongs entirely to the uranium. This unique chemical compound serves as the standard feedstock that makes commercial enrichment facilities possible. The centrifuge spins the gas at supersonic speeds, pinning the heavy uranium-238 to the wall, while the lighter uranium-235 remains centered. But a single machine has severe limits. One pass through a centrifuge only increases the uranium-235 concentration by a fraction of a percent. To solve this, thousands of machines are piped together into a massive interconnected cascade. As the gas is pushed through this continuous loop, the concentration slowly builds, eventually producing low-enriched uranium at a concentration of 3 to 5%. This output is what provides the safe, commercial power generation used in a standard civilian reactor. Mastering this mass separation provides our energy, but as the isotopic purity scales up, it introduces a dangerous new physical hazard. Operating these facilities requires constant monitoring for a criticality accident, an uncontrolled chain reaction. The amount of material needed for this to happen drops as the enrichment level rises. At 5% enrichment, it takes over 800 kilograms to reach a critical mass. But at 90% enrichment, that threshold drops to just 20 kilograms. Handling this material requires safe geometry engineering. Equipment must maximize surface area, forcing neutrons to escape the material before they can trigger more fissions. This is visible in the shipping protocols. Standard reactor fuel is shipped in 30-inch cylinders, but weapons-grade material is restricted to these narrow 5-inch cylinders to prevent a critical geometry. The laws of physics dictate that the higher the enrichment, the more strictly engineered the physical environment must become. Historically, uranium enrichment required massive gaseous diffusion plants that stretched for miles, making them difficult to hide. Modern centrifuge plants are much smaller and require less electricity, meaning they are significantly easier to conceal from satellite reconnaissance and energy grid monitoring. This creates the dual-use dilemma. the exact same facility and cascade architecture designed to produce fuel for civilian reactors can be reconfigured to produce weapons-grade uranium. Because the technology is identical for both peace and war, external oversight is the only way to verify a facility's true intent. That oversight is the responsibility of the International Atomic Energy Agency. They maintain a regime of continuous monitoring and physical inspections at sites across the globe. They use tools like the OLAM system, which measures real-time gamma-ray flux in the pipes. This allows inspectors to verify that a civilian plant isn't being secretly reconfigured for military use. Our ability to harness the highest energy density on Earth depends entirely on monitoring and safeguarding the microscopic mass of a single atom.